Hello and welcome. Today we are diving into something that sounds complicated but is actually kind of magical: statistical inference. This is all about how we can know things about a massive group, like, say, all the voters in a country, just by looking at a tiny, tiny little piece of it. So, how on earth is that even possible? Let's find out. Okay, so let's start with the classic mystery, right? You see it all the time. How can a poll of just 1,000 people possibly predict what millions are going to do in an election? It feels impossible, like trying to figure out what the entire ocean tastes like from a single drop of water. But believe it or not, it's not magic. It's statistics, and we're about to pull back the curtain.
At its heart, the challenge is this. We desperately want to know the truth about a huge group. That's what we call a population. But, we can't talk to everybody. We can't test every single light bulb. So all we have are clues from a small, manageable group, and we call that a sample. Statistical inference is basically the detective work of using those clues to figure out the truth.
Now, this basically lays out our whole detective story. On one side, you have the parameter. That is the truth we're hunting for, the real average, the real percentage for the entire population. It's a fixed number, but it's hidden. Then, on the other side, we've got our clue, the statistic. This is the number we actually calculate from our sample. We can see it, we can touch it, but it changes every time we take a new sample. The whole game is using our clue, the statistic, to make a really, really good guess about that hidden truth, the parameter.
So, just to be super clear, the population is the whole shebang. It's everyone or everything we are curious about. All the students in the university, every light bulb that rolled off the assembly line, every single car in the country. It is the big, big picture.
And the sample? Well, that's our handful of clues. It's a small, carefully chosen slice of that big picture. Instead of trying to talk to all 30,000 students, we survey 500 of them. Instead of testing every light bulb till it pops, we just test a batch of 100. It's the part we can actually get our hands on and study. Okay, so we've got our clue, but you might be thinking, how can we possibly trust it? I mean, how do we know our little sample isn't just weird, a total fluke? Well, this is where the real beauty, the real logic of sampling comes into play, and it's all built on one incredibly powerful idea.
So, the secret bridge connecting our tiny clue back to that giant, unknowable population is this amazing concept called the sampling distribution. Now, stick with me here. It's a bit theoretical, but it is the absolute foundation, the bedrock, that makes all of this work.
To really get this, let's make it super simple. Imagine our entire population is just 4 students, and their test scores are 4, 5, 6, and 7. Now, what if we took every single possible sample of 2 students? Well, you could get a 4 and a 5, their average is 4.5. You could get a 6 and a 7, their average is 6.5. You could even get a 5 and a 6, their average is 5.5. What you start to notice is that some averages, like 5.5, pop up more often than others. When we graph how frequently each of these possible sample averages appears, boom, that picture, that pattern, that is the sampling distribution. It's a map of every possible outcome we could have gotten from our sample. And that brings us to the hero of our story. The reason this whole thing works so well in the real world is because of a fundamental rule of the universe called the central limit theorem. And honestly, it might just be the most important, most powerful idea in all of statistics. And here's the magic trick. The central limit theorem, or CLT for short, says that it doesn't even matter what the original population looks like. It could be totally weird and skewed, but if you take samples that are big enough and you plot out their averages, that pattern, that sampling distribution, will almost always form a beautiful, predictable, symmetrical bell curve. It's this amazing predictability that gives us the power to be confident in our guess from just one single sample. So now that we know our clues follow a predictable pattern, thanks to our hero, the CLT, we can actually start building our case about the real world. And when we do this, there are basically 2 main tools in the statistician's detective kit. The first tool is called estimation. This is pretty straightforward. It's where we say, okay, based on our sample, here is our best educated guess for the true value of the whole population. The second tool is called hypothesis testing. And this is where we put a specific claim on trial. Like, is this new drug actually more effective? Or is the average weight in these bags of chips really what the company claims it is? Now, with estimation, just giving one single number as your guess can be a little bold.
it's probably not exactly right. So a much more honest and, frankly, a much more useful approach is to create a confidence interval. Instead of just saying, our best guess is 10, we build a range around it. We say, you know what, we're pretty confident the true answer is somewhere between 8 and 12. It's like an estimate that comes with a built-in dose of humility, which is good because it acknowledges the uncertainty we have from just using a sample. So what does 95% confident really mean? This is so important. It means that if we were to do this whole process over and over again, take 100 different samples and create 100 different interval ranges, we would expect the true hidden population value to be caught inside our range about 95 out of those 100 times. Our confidence is in the method, not in this one specific range we just calculated. And here it is, the single biggest mistake people make with this. You cannot say, there's a 95% chance the true value is in this range. That's wrong. Why? Because the true value for the population isn't moving around. It's a fixed number. Our interval, which is based on our random sample, is the thing that's moving. Think of it like a ring toss. The post is fixed. The 95% refers to our skill in tossing the ring, not the chance that the post will jump into our ring. Okay, let's switch gears to our second big tool, hypothesis testing. And honestly, the absolute best way to think about this whole process is like a courtroom drama. We're putting a claim on trial, and our sample data, that's the evidence we're presenting to the jury. So in our courtroom, you've got two opposing sides. First, there's the null hypothesis. Misses the defendant. It's the status quo, the innocent until proven guilty idea. It basically says nothing interesting is happening here. Then you've got the alternative hypothesis. This is the prosecutor making a bold claim. This is the idea we're actually hoping to prove with our data. Like, no, this new drug does have an effect. And the whole procedure follows this really logical courtroom-style process. Step 1, you state the accusation. That's the null hypothesis. Step 2, you set the standard of proof. How strong does the evidence need to be? Step 3, you examine the evidence you've collected from your sample. And finally, step 4, you deliver the verdict. Is the evidence strong enough to reject that initial assumption of innocence? Now that standard of proof has a name. It's called the significance level, or alpha. A very common value is 0.05. What this means is we're setting the bar for evidence pretty high. We are only willing to accept a 5% risk of making a very specific kind of mistake, a type 1 error. That's where we reject the null hypothesis when it was actually true. In our courtroom analogy, that's like convicting an innocent person. We have to decide on that acceptable level of risk before the trial even starts. So, after all the evidence is collected and all the rules of the court have been followed, we can finally reach a conclusion. We can move from just having a small clue to making a powerful, data-driven decision about the really big picture. So, if you remember one thing, let it be this. The crucial point is that statistical inference is the toolkit that lets us build a bridge from the small, manageable sample we can actually see to the vast, unknowable population we care about. It's what gives us the power to make these incredibly strong, reliable conclusions about the world without having to measure every single thing in it. And that's our look at statistical inference. From calling elections to making sure our medicine works, these are the tools we use to understand the world through data. So now that you know the basic framework, what's a widespread belief or a common assumption that you would want to put on trial?